Good day, everyone, and we meet yet again. And today we're going to cover energy, power, and cost in circuits. Okay, so essentially nothing changes when it comes to Ohm's law and all the things that we've learned so far about how we treat circuits. But I just want to focus a little bit on how we calculate energy and power. And for those of you who are doing the IEB and other examinations around the world, that have got calculations on cost. Perhaps this will be more relevant to you. For those of you doing the NSC exam in South Africa, please don't worry about that section, but however, you will still benefit from energy and power nonetheless. Okay, so let's get into it. If you haven't subscribed, well, welcome to the family. Okay, please don't forget to hit that thumbs up button. Okay, if you like this lesson. All right, let's get into it. So we've spoken at length about electrical circuits, right? And obviously, we're given different things about a circuit. Okay, so if we've got a resistor, an external resistance, whatever it is that we may have in the external circuit, right? We know that there's a current that is flowing, and we also know that there should be a potential difference across that particular resistor, right? Now, what the battery does is that the battery supplies us with electrical energy, okay? And in this case, we know that current will therefore flow into the external circuit, and as a result, whatever it is that we have in the external circuit consumes the energy. So this one supplies the energy, and that energy is therefore consumed by the external devices. Okay, so now when it comes to energy in electrical circuits, we've got an equation that says energy, that is the work done, will be the voltage multiplied by the current multiplied by the time. Now I need to give a warning for this one. Okay, please note in this case that the time is measured in seconds. Okay, right, so you've got voltage multiplied by current multiplied by time. Now I want you to please note, for a particular circuit, if you remember what I said, right, that we always use voltage with its corresponding resistance. So if I wanted to find out the work done or the energy, okay, across resistor R external, so in this case, the voltage there should be the voltage across that particular resistor. You'll see in just a moment when I take a question. And what I'm going to do is just adapt it a little bit so that we take more of these kind of questions. Okay. So now, by the way, we also know that energy, so there are three equations for energy, but you know that voltage is voltage equals to current multiplied by resistance, isn't it? This is according to Ohm's law, right? So I can actually replace the voltage here with I multiplied by R multiplied by I times T, okay? So still the same equation, and what do I have? I end up with I squared R multiplied by T. So now, please note, if I wanted to find out the energy across a particular resistor, I must actually take the current that is passing through that resistance multiplied by the particular resistance of the resistor multiplied by time. And once again, time is in seconds, right? So in this case, just to take the last one, okay? So from the same equation, you can say, well, but we know that current is V over R, isn't it? Okay, so instead of substituting there for voltage, let me substitute for current. Okay, so you end up with V multiplied by V over R times T. So all I'm trying to do is just to show you where these come from. But nonetheless, ladies and gents, please, you will not be required necessarily to derive these equations. You just need to know how to use them. Okay, so I'm going to show you from a question paper that, by the way, you actually have all of those formulas. Okay, let me just head over to the electricity part. Okay, so if you look at on this side, right, so that's VI delta T, so voltage current change in time, that's that I squared R times delta T, V squared delta T over R. So you do have those equations available to you. Okay, so you don't need to necessarily worry about it. Okay, now, so by definition, we say that now we've just found three equations for energy, right? Or rather, we just shown you that there are three equations for energy. Okay, so now what we want to find is, we want to now define power. Now we say power is the rate at which work is done, isn't it? So power will always be, when we say rate, it's always division by time. Okay, it's the rate at which work is done. So the power across a resistor is the rate at which it consumes energy, right? So as a result, it's going to be the energy of the particular resistor divided by time. Now notice what that does. Okay, if you remember that energy is VI, okay, I'll use that delta T designation there, divided by delta T. Look at what this does. Okay, you can cancel those two, so power in effect now becomes V multiplied by I, right? But obviously, just like we did for energy here, you can now have, remember we said energy I squared R multiplied by T. So you can say, well, it's going to be I squared R multiplied by T divided by T, and you end up with I squared R. Okay, so that would be power. Okay, and obviously the last one where you've got V squared divided by R. Okay, so essentially when it comes to power and energy, this is what you are going to have. Okay, right, if you don't mind, what I'm going to do is I'm going to reserve the part about cost as the last part of it. Okay, as the last part of this video. Okay, so what I want us to do is just to try and express this in an electrical circuit. Just try to do questions that are related to energy and power. Okay, shall we do that? Right, so let's take the simplified circuit. Right, so we're given the circuit with an EMF of 12 volts and an internal resistance of 2 ohms, right? And they connected to that external circuit and the switch is closed over there. Okay, so if you haven't watched the circuits that have switches on them, obviously just refer back to the previous lesson. Right, now if you look at this, they say to you calculate the reading on A, right? Of course, many of you would know how to do this by now. Okay, we said voltage where there's corresponding resistance. Now, if you note there is no other voltage that is given except the EMF. And we know in this case, I'm just simply going to say, okay, if I take the EMF, so I'm going to take the EMF equation and say E is equals to I into R plus small r. Now, if you remember, ladies and gents, looking for the reading on A, okay, I know that total current, okay, obviously current will move, total current will move across the 12 ohm resistor. When we get to this node, the current is going to split, so some of the current will go there. So let's call that current I1, let's call that current I2, okay, and we know when we get to that node, both I1 and I2 would pass here. In the form of the total current. So in effect, when they said calculate the reading on A, they are looking for the total current in the circuit, right? So now we go to that equation and we say, okay, we know the value of the EMF is 12, okay? We want to find the total current. Now, please remember when you use this equation, it simply means that that value there will be the value of the total current, right? So that's the one that we want. Okay, what does R, by the way, what does R stand for? okay, that will be the internal resistance, right? So in this case, want to make sure that we get, rather the external resistance. So what would be the external resistance of the circuit? So what you simply are going to do, okay, I'm going to do it on the side here. So we take that R parallel, the effective parallel resistance. And by the way, there's a shortcut where you just simply say R1 times R2 divided by R1 plus R2. Okay, so that's going to be 18 times 6 divided by 18 plus 6. Okay. Okay, and I simply get a value of 4.5 ohms. Okay, so it means that my parallel resistors give me an effective resistance of 4.5 ohms. Now, if you remember what we said previously is that to get the total or the effective resistance in parallel, that effective resistance should be smaller than your smallest parallel resistor, right? So in this case, definitely 4.5 is less than 6. Okay, so that looks about right. So what we've done now is to make that circuit such that now you only have two resistors, okay? And the one resistor is the 12.5 and the other resistor is the 4.5 ohm resistor, okay? Now, once again, which current passes across the 12 ohm resistor? This should be, oh, did I say 12.5 there? That's 12 ohms rather. So that's 12 ohm resistor and the 4.5 ohm resistor. So total current passes across the 12 ohm. Total current also passes across 4.5. So in fact, it simply tells you these two resistors are in series. So it means that the total resistance of your circuit should be 12 plus 4.5, and that should give me 16.5. So it means that I'm going to put 16.5 there. Please keep that in mind, ladies and gents. Okay, as you do circuits, right, please remember that that current there should actually be the total current, right? And then we were given also the internal resistance, which is 2, okay? And all that's left for us to do now are some gymnastics mathematically. So we're going to have 12 divided by, when I add these two, are going to give me 18.5. So I get a total current of 0.65. Okay, I'm rounding it off. Okay, so my total current is going to be 0.65 amperes. Okay, right. Now the second question says to us, calculate the energy dissipated by the 12 ohm resistor in 5 minutes. Now notice, ladies and gents, when we want the energy, because that's what we want to find, isn't it? When we want to calculate the energy, all that we simply do, remember that we've got 3 of those equations. You remember them, right? Now, let's go to the resistor in question. What do I have about the 12 ohm resistor? Do I have the voltage of the 12 ohm resistor? No, I don't, right? So then I wouldn't want to use an equation that would, or rather, we're looking for energy. So I wouldn't want to use an equation where I would have to use voltage. So this one would be a no-go, right? But I would say, well, what do I have about the about the 12 ohm resistor? I know the current that's passing there, isn't it? Because it's the same current as that current that passed there. It's the total current. So now I'm going to say, well, it means the energy dissipated by the 12 ohm resistor. So which of the 3 equations, okay? Remember the 3 equations I showed you? Which ones have current and resistance? Remember, we've got the resistance of the resistor. So of the 3 equations, there it is, I squared R multiplied by time. So I'm going to go for that one and say, well, I actually want one that's going to avoid using the voltage. So that's I squared R multiplied by the time. Okay, my current passing through the 12 ohm, that's 0.65 squared multiplied by the resistance there, that's 12 multiplied by the time. Now remember, I said that time must be in seconds, right? Please keep that in mind. Okay, So because time must be in seconds, it means I must convert those minutes into seconds. And how do I do that? Remember that you've got 60 seconds in a minute, in 1 minute. So therefore, if I've got 5 minutes, it's going to be 60 multiplied by 5. Okay. So as a result, let's calculate that quickly. Okay. And I simply calculate it and I get 1521. And please remember that energy is measured in joules. Nothing changes, right? So we measure energy in joules. You can verify that for me, okay, and see if you get to the same answer. Okay, and here's the last question. So they say to you, calculate the total power delivered by the battery. Okay, now remember, once they say to me it's the total power, it should also include the power that is obviously dissipated or consumed rather by the internal resistance, right? So it means in this case it's going to be, I know that power is the rate at which work is done. Okay, but remember, once again, I've got 3 equations for energy, right? Or for power. So that's V times I. I've got another one, I squared R times T. Okay, P, and then P is equals to V squared over R multiplied by T. Now I want you to please note, ladies and gents, okay? Now, do I have the resistance of the battery? Absolutely not. And it is not the internal resistance. Note that they said calculate the total power. Okay. So in this case, these two formulas would not be applicable, right? Why? Because I wouldn't have the resistance in that case. So I'm going to stick to the one that says, well, it's voltage multiplied by current. The question is, right, if I wanted the total power, okay, which voltage am I going to use? And I'm sure someone has already thought of it. Of course, I'm going to use the EMF there. So it's going to be V times I, but the voltage that I would use there would be the voltage of the EMF, okay, or it's going to be the EMF rather. Okay, and what is the current that's delivered by the battery? Okay, of course it's the total current. It's the one that we calculated before. So that's 0.65, and what we get there, so that's 12 times 0.65, and we get a value of 7.8. And please note, because we are talking about power, this is simply 7.8 watts. Okay, so these are 7.8 watts of power. All right, so in effect, you know what, let me just do something with you. So what if I wanted to find out, okay, what is the power delivered by the 18 ohm resistor? Okay, I'm just throwing it in there so that I show you how you would go about answering that question, right? Okay, I'm just going to reserve some little bit of space there. So what if I wanted you to calculate the power, okay, dissipated by the 6 ohm resistor? Okay, now you'd say to me, well, for the 6 ohm resistor, I don't know what is the current I2, isn't it? Okay, but my question is, would it be possible for me to calculate the voltage across the 6 ohm resistor? Now, obviously, of course, I know you guys are now proficient on circuits. Okay, so you'd say, remember we converted that into that one resistor there, which is 4.5, isn't it? So which current is passing through that one resistor there? The current that is passing through the 4.5 ohm resistor would be, in this case, the total current. Okay, so can I find the voltage here? Absolutely. So let's find the voltage. Let's call it V parallel. Okay, so this is going to be I total multiplied by my parallel resistor. Okay, so I'm going to say, well, my V parallel there is simply going to be 0.65, okay, multiplied by my R parallel, in this case, which was 4.5. Okay, so that would be the voltage. Now I want you to note, so 0.65 times 4.5, and that would give me 2.925. Okay, let's say 2.93. Okay, I'm just rounding it off to 2 decimal places. So this would be 2.93 volts. Okay, so it means that the voltage across my parallel resistors, right? Now, what do I know is 2.93 volts, that is. So what do I know about resistors in parallel? We said that voltage is the same. So the voltage over the 4.5 would be the same voltage across the 18 as well as the voltage across the 6 ohm resistor. So now that I know the voltage there, okay, can I calculate the power? Well, we'll say, well, I'm going to look for an equation of power that has voltage and resistance. Can you see that? Okay, so that's the advantage about energy and power, because you can actually play around with those resistors, right? With those formulas. Okay, so it means that simply say, so power, I'll take the one that says V squared over RY. I'm avoiding the one that has that would want me to calculate current first. And so as a result, I'll just simply say power would be V squared. Okay. So that would be, my voltage is 2.93 squared, okay, sorry about that ugliness there, divided by the resistance of it, okay, which is going to be 6. And in this case, you would find that value for power there. Okay, let me just square that value, okay, and divide that by 6, and you get a value of 1.43. Okay, and please remember that power is measured in watts. Okay, so that power there is measured in watts. I hope that makes sense, ladies and gents. Okay, right, so in this case, we know if we wanted to find the power, you can use any of the 3 equations that you are given there. Okay, and you can calculate the power in that way. Okay, of course there are some instances. Okay, let me just show you just one instance where you were given an electric circuit. Now, I'm not going to go through the entire circuit, but I want you to see it for yourself. Okay, this was in the 2019 paper. Okay, where they had actually given you 2 things there. They gave you a circuit. Please have a look at that question if you can. All right, they gave you a circuit and they gave you the power rating as well as the voltage across that particular those light bulbs. Okay, and in this case, what they wanted you to do is to find the resistance there. So obviously you've got the power, you've got the voltage, and you want the resistance. So obviously, which one would be best to use? It would be V squared over R, right? You've got the power, you've got the voltage, and you've got the you're trying to get the resistance, so you would be able to get it that way. Okay, right. So you know what? I am thinking for those of you doing IEB, I'm just going to do a separate lesson. Okay, that's particularly on cost, how to calculate the cost, rather than maybe to include it here. Okay, so just look out for that. Probably I will have it available as soon as I can. Otherwise, ladies and gents, I hope this lesson, very short lesson, has been helpful, and it will now enable you to answer questions that are based on work and energy when it comes to electrical circuits. Otherwise, please don't forget to give that thumbs up. All right, and don't forget to subscribe for those who haven't, and I'll see you guys another time. Thank you so much. Sharp, sharp.